Now, what is really quite interesting to see is the frequency response of the amplifier. I'd like to show you what the gain looks like across a wider range of frequencies. So first of all, let's go on to project options and then select a starting frequency of 0.1 GHz, a stop frequency of 4 GHz and a step of 0.01 GHz. Then click on Apply and OK. Then go to Graphs, select a new graph. It will be a rectangular graph and we'll call it gain versus frequency. Then we right click, go on to add a new measurement, and this measurement will come from a matched schematic, of course. We want to see the S21 in dB across a range of frequencies, so we'll use the sweep frequency for the x-axis. Click on Apply and then OK. Then Simulate. Now you can see the gain profile of our transistor, and you can see that we have a good amount of gain at lower frequencies, and then we roll off really steeply after the center frequency for which we've designed, and then come back up to some extent. Of course, we could display this graph also in a logarithmic fashion, but I'll keep you to a normal linear fashion for now, because I'd like to talk a little bit about the two troughs that you see on the graph. First of all, let's look at what frequencies those troughs occur at. So let's press Ctrl M and then click on the graph, and let's move our cursor to the first trough. And you can see that this occurs at a frequency of 2190 MHz. Then we can add another marker by pressing Ctrl M and clicking on the curve yet again, and then we can move this down as well to the bottom of this dip, and you can see that this occurs at a frequency of 2480 MHz. So where do these come from, and could we actually predict them? Could we predict that we have a sort of low pass response for our amplifier? Well, the answer is yes, we could have done. Let's go back to our matched transistor schematic. Now, when we look at these matching networks, we have to remember something that we saw in previous tutorials. We saw that an open-circuited stub of an electrical length which is lower than 90 degrees behaves effectively like a capacitor. So what we've got in our matching networks, in both of them, is a shunt capacitor. These capacitors will have high impedances at lower frequencies, and hence they will not take power away from the high frequency signals. But when we go up to higher frequencies, the capacitors will have a lower and lower impedance, and hence the high frequency energy will actually be sunk into those capacitors, and therefore this matching network have a low pass behavior. Both of them do. So the low pass behavior which we see here is totally predictable. But what about these troughs? Where do they come from? Well, this can again be explained by looking at our open-circuited stubs. These open-circuited stubs have got an electrical length of 69 degrees at 1900 MHz and 78 degrees at the same frequency respectively. But as we go up in frequency, as we know, the electrical length will become longer. For example, for the input, an electrical length of 69 degrees and 1900 MHz will translate in a greater electrical length as the frequency increases. If we go back to our gain versus frequency graph, the electrical length of 69 degrees at 1.9 GHz corresponds to an electrical length of 90 degrees at 2480 MHz. So this means that whereas at 1.9 GHz my open-circuited stub has an electrical length of 69 degrees at 2480 MHz, it will have an electrical length of 90 degrees. Now remember that this stub is open-circuited at one end. So if this becomes 90 degrees, which means it's a quarter wave transformer, the open circuit that we see here will become a short circuit here. So a high frequency signal with a frequency of 2480 MHz will see this branch as a very low impedance branch, and hence all the energy will be sunk into it. So this explains this trough here at 2480 MHz. So what do you think causes the other trough? Well, if we go back to the schematic again, we can work out that the stub that we've got at the output, the open circuited stub, which has got an electrical length of 78 degrees and 1.9 gigahertz, turns out to have an electrical length of 90 degrees at 2190 megahertz. So this means that at this very point here in frequency, our open circuited stub again behaves like a quarter wave transformer, and hence at this point here a signal of a frequency of 2190 megahertz will see very low impedance, and hence will be sunk into here, and that is the reason for the massive reduction in gain and the trough that we observe in the gain versus frequency curve. So we've explained why we have a low pass behavior, because the open circuited stubs behave effectively like capacitors, and hence our matching networks have a low pass nature. And also we've explained why when we have an open circuited stub with an electrical length of 90 degrees, this stub effectively turns the open circuit into a short circuit at the point where it is inserted, and hence becomes very low impedance and can sink a lot of energy at the frequency at which its electrical length is 90 degrees. Now lastly, what I'd like to do is carry out the match with short-circuited stubs, but still fully with transmission line elements, and see how this changes things. So let's go back to our input match schematic, and now what we're going to do is replace the open circuited stub with a short-circuited stub. We'll set its frequency to 1900 MHz, and also we'll double click on it, and we'll make it tunable. We'll tune it between 0 and 180 degrees in increments of 1, and we'll leave its electrical length to 90 as an initial value. That's actually quite a good trick, and I'll explain to you in a second why that is. Click on OK. Remember that if this is 90 degrees, we have a quarter wave transformer. So if this is a short circuit here, then on the other end this is an open circuit, and this means that initially if we choose a value of 90 degrees, this will have no effect whatsoever. If we chose a value of 0 for a short-circuited stub, this would be a short circuit to ground, and hence you'd start from another point on the chart. You start from the short circuit point. So to start from the point that you're actually at initially, which is your 50 ohm source impedance, you need to set the initial value of a short-circuited stub to 90 degrees, and for an open-circuited stub to 0 degrees. Then also we double-click on our transmission line. We set the initial value to 0 in this case, and we've already got all the tuning values in there already. Click on OK. Then of course we need to go to project options, and again select to have a single point of 1.9 gigahertz. Click on apply, and then OK. Now let's simulate, and let's go back to our input match Smith chart. You can see that now we are exactly at the same point as we were before, and that's because we used that trick of having the short-circuited stub being 90 degrees as an initial length. So let's open the tuner, and as before, what we need to do is work out a length for the short-circuited stub, which is TL1, to get to the intersection of the constant conductance circle and the constant gamma circle. So we'll start decreasing the value of our stub until we get to a point where we meet the constant gamma circle, and that's 21 degrees. Then we'll start increasing our transmission line length until we get to our desired point, which happens for a length of 25 degrees. So that is our input match sorted. Now let's close the tuner, and let's go to our output match. Again, we need to replace the open-circuited stub with a short-circuited stub. We'll leave its initial length to 90 degrees for reasons we've just explained. Set its frequency to 1900 MHz. Double-click on it. Make it tunable. Go between 0 and 180 in increments of 1, and then click on OK. Then we go to the transmission line and we set the initial values to 0, make it tunable, and again we've got the limits in there already. Click on OK, and then simulate. Now let's go back to our output match Smith chart, and you can see that we are in the same pre-match situation as we were before. So now I can open the tuner, and TL1 yet again represents my short-circuited stub. So I'll start decreasing its value until I find the intersection with a constant gamma circle, and this happens for a length of 12 degrees. And then I can start increasing the length of the transmission line until I get myself to the target point, which happens for a transmission line length of 61 degrees. So that's our input and output matching networks sorted when using transmission lines with short-circuited stubs. So let's close the tuner yet again, and as we did before, we will create a copy of our S-parameter schematic, because we don't want to meddle with it or with the one which has got open-circuited stubs on it, so we can actually do a comparison. So let's right-click and then go to Duplicate Schematic, and then we click on the name of the new duplicated schematic and select Rename, and we go for S-parameter measurements matched SC. And now we make a little bit of space here, and we go back to our input match schematic and copy our matching network and paste it to the amplifier schematic. Put it in series with the input and reconnect everything. And then let's go back to our output matching schematic, and again we get the matching network from there. Press Ctrl C and then Ctrl V and place this at the output of our transistor and reconnect everything together. Now, do you actually think that this is going to work the way it is? I'll give you just a second to think about it. Well, the answer is no, because you always have to bear in mind what's happening in terms of your DC bias. This transmission line here will have its own impedance at high frequency and all that, but it's nothing but some metal going down to ground for our DC circuit. So this will take your bias down to ground and hence completely mess with it. Same thing for the output. So you've got to be very careful with this sort of thing, because if you have a short-circuited shunt stub in a matching network, or equally if you have an inductor in shunt with a matching network, then you have to make sure that the bias of your transistor is not affected. And how can we do that? Well, we can just use one of the DC blocking capacitors. So let's make a little bit of space here and then remove this connection and press Ctrl C and Ctrl V and copy this capacitor over here and put it in series with our stub. This capacitor, as we know, will not affect the operation at our frequency of interest because it's effectively a short circuit. But at DC it's an open circuit, so our short-circuited stub won't affect our bias this way. And we can do a similar thing for our output short-circuited stub. So now, first of all, we need to verify that the performance of the amplifier with its new matching networks in is what we expect. So let's go on to graphs and then create a new graph. It'll be a tabular graph yet again, and then we'll call it S-parameter TLSC. And then we'll right-click, go on to add a new measurement. We'll start from the S21, the gain, coming from the S-parameter matched with the short-circuited stub schematic. We want it as magnitude in dB, click on Apply. Then we look at the S11, but in normal form, click on Apply, and then S22 as well, click on Apply, and then OK, and then simulate. And you can see that the gain is not as good as we had with the previous configuration. In fact, we could easily compare the two by going on to Windows, Close All, and then just opening the two S-parameter graphs, and then selecting Window, Tile Horizontal, and if we adjust these a little bit, we can see them a bit better. And you can see that we had a gain of 17.7 before, and now we have about 17.2. But equally, you can see that the S11 and the S22, so the reflection coefficient and input and output, are actually lower when we're using the short-circuited stub matching network rather than the open-circuited ones. But at least we can be reassured that we have actually improved the performance of the transistor and things seem to be happening in the way they should. Now let's go back to project options and then let's set up a frequency sweep yet again. So we'll untick single point, we go from 0.1 GHz to 4 GHz, click on apply and then OK. And then we will go back to our gain versus frequency graph, and then what we're going to do is add a new measurement on it, which will be again S21, but this time it will come from the schematic where we've used the short-circuited stubs. Again, we want it as a magnitude in dB, click on apply and then OK. Then simulate. Let's move the legend out of the way and also let's remove these markers. And now you can see that we have quite a different response. I'd like to change the thickness of the lines on the graph so they become a little bit more visible. So we just right click, go on to properties and then traces, and I'll select the thickness of the line for the blue curve to be a little bit bigger, and also that for the pink curve to be more or less the same thickness. Click on apply and then OK. Right, now we can see them a little bit more clearly. Now, we've seen these two troughs here and we've explained where they come from. We've also explained how when we use open-circuited stubs, we end up having a low-pass response for our gain. In the case of short-circuited stubs, we are quite in the opposite position, in that we have more of a high-pass response. And again, we have a couple of troughs. Where do these come from? Do they come from the fact that the short-circuited stubs become 90 degrees? Well, this is a bit trickier circuit to work out. So let's go back to it and let's get going with the reasoning. In this case, we've got these two short-circuited stubs. Now, two things I want to point out. First of all, if this stub becomes 90 degrees at some higher frequency, what will happen? Well, this is a short circuit here. So if this is 90 degrees, we end up with an open circuit over here. But if this is an open circuit, then any high frequency signal that tries to go down it will not actually have a low impedance path to be sunk into. So really, it won't really affect things at all. This will just be a path that the high frequency signal will not follow. Identical reasoning for the output short-circuited stub. The other thing is that if we look at the frequencies at which our troughs occur, and we can do this by pressing Ctrl M and inserting a couple of markers and then moving them to the bottom of these troughs, these frequencies are actually lower than our center frequency. So, since the electrical length of a stub is directly proportional to frequency, if a stub is 21 degrees at 1.9 GHz, it'll be way less at 820 or 1020. And for the output stub, which is only 12 degrees, then that will be a tiny electrical length at lower frequencies. So definitely we can't possibly blame these two troughs on a quarter wave transformer effect. So the devil is in the details this time, and it comes from a very, very simple fact. Whereas before we had an open circuited stub in shunt, which meant effectively that we had a capacitor in shunt in our matching network. In this case we have short-circuited stubs in shunt, and remember that short-circuited stubs behave like inductors if their electrical length is less than 90 degrees. So effectively those two short-circuited stubs are acting like inductors since their electrical lengths are less than 90 degrees. Now, if in a branch you have an inductor in series with a capacitor, guess what's going to happen? You're going to have resonance. So there's going to be frequencies at which the capacitors and the short-circuited stubs, which behave like inductors, will resonate, and hence you will have a very low impedance path to ground, which will sink the high frequency energy at that particular frequency at which resonance occurs. You don't believe me, do you? Well, let's prove it. Let's take this branch here and copy it by using Ctrl+C. Let's open a new circuit schematic. We'll call it input resonance. And then let's copy this branch right here. Then let's add a measurement port, and we'll connect it right to the point where this branch of the matching network is connected to the source. Now let's go to graphs, open a new graph, and it'll be a Smith chart, and we will call it input resonance yet again. And then we can right click and select add a new measurement. Of course, the measurement will come from the input resonance schematic. We want to see the S11, so click on apply and then OK. The S11, of course, gives us the impedance seen by port 1 on a Smith chart. And click on simulate. Well, you can see that this is just a series resonance circuit. We've seen identical graphs to these in previous tutorials, and this resonance circuit is capacitive at lower frequencies, and then it reaches resonance right here, and then is inductive at higher frequencies. So if I just press Ctrl+M and then put a marker right here, you can see that our resonance, which occurs when the impedance of the branch is very low, virtually zero, and is purely resistive, is around 820 megahertz. So if we go back to the gain versus frequency graph, guess when one of the troughs occurred? 820 megahertz. So there, I guess I've proven my point here. I could do a very similar thing for the output one, and in fact we might as well do it. Let's go back to our amplifier schematic, and this time grab this other branch, press Ctrl+C, create a new schematic, and then we'll call it output resonance this time. And then we can copy the branch right here, insert a measurement port, then connect it so that we can see the impedance versus frequency of this branch. And then we can go back to graphs, create a new graph, it'll be a Smith chart. We'll call it output resonance, and then we right click on the chart, add a new measurement, it'll be the S11 yet again, and it'll come from the output resonance schematic. This will allow us, since we have a Smith chart, to see the impedance of this branch versus frequency. Click on apply and then OK. Then simulate. And again we have a resonant frequency somewhere around here. Let's press Ctrl+M, add a marker on this curve, and then slide it down a little bit. And you can see that our resonance occurs at 1020 megahertz. At this point we are on the resistive axis, on a very low resistance, and we have a purely resistive impedance, since the reactive parts of our impedances cancel out. So if we go back to our gain versus frequency graph, now we've explained where these two troughs come from for our short-circuited stubs matching network. Very last thing, I promise, I'm going to go back to the schematic where we use the short-circuited stubs, and I will remove this DC blocking capacitors and show you what happens if we do remove them. So remember, you need these both if you have short-circuited stubs and if you have inductors in shunt in your matching network. So let's just remove these two and just replace them with a little bit of wire, and then click simulate. Let's take a look at the gain, and as you can see, the gain has absolutely plummeted. In fact, if I click on this marker and use marker to max, you can see that the maximum gain that you get is minus 13.18 dBs. So instead of getting gain, you're actually getting some attenuation. This concludes our tutorial on simultaneous conjugate match for BJTs.